In this video, we will look at the steps necessary to do stoichiometry in a redox reaction. But before we start, let's remember that stoichiometry, the calculation of matter in chemistry, can be used to actually predict or analyze any given solution or material. And there's many different applications, so we could do this in labs, techs, hospitals, environmental chemistry, solution chemistry, and even in everyday life as well. So let's look at an example. We have an acidified, and again acidified means the presence of hydrogen ions, crushed silver ore. Silver ore is a solid mixture, a heterogeneous mixture of solid silver with rocks, with an original mass of 104.7 grams, required 21.6 ml of a 0.459 mole per liter potassium dichromate solution for it to reach the endpoint. And we're asked to find what the mass of silver was actually present in the ore. As with all stoichiometry, we're going to need to calculate or determine a balanced chemical equation. In order for us to determine the balanced chemical equation, we need to identify what is the strongest oxidizing agent and the strongest reducing agent. As from previous samples, we have to first identify all the species that are present and list them as either a reducing agent or an oxidizing agent. Here we have hydrogen, because in an acidified solution. We have solid silver, a whole lot of water, some potassium, and dichromate. We find that oxidizing agents are hydrogens, water, potassium ions, and dichromate. And our reducing agents present are silver solid and water. However, when we look in our table of reduction half reactions, we find that our strongest oxidizing agent is an acidified solution of dichromate, and our strongest reducing agent is silver. So we look at a half reaction and we read the reduction half reaction for dichromate, and it is dichromate plus 14 hydrogens plus 6 electrons to yield 2 chromium 3 plus and 7 waters. The oxidizing reaction or reduction agent, we read the reactions in reverse. It's silver solid becoming silver ion and 1 electron. So we look at our reduction half reactions. We notice in our reduction equation we have 6 electrons. However, when we read our oxidation reaction, we have 1 electron. We need a lowest common multiple of 6 electrons. So therefore we need to multiply our oxidation reaction by 6. So we have 6 silver solids, 6 silver ions, and 6 electrons. We add our equations together, and this is our final result. Once we have this balanced chemical equation, we can now do the stoichiometry part. Now our question asks us what mass of pure silver was present in our ore. So the first thing we need to do is calculate the moles of dichromate present. And to do that, we have to do or use the formula N equals CV, because it was a solution of potassium dichromate. Our concentration was 0.459. We used 21.6 milliliters. So then the total moles of dichromate present is 0.00991 moles. Then we use the mole ratio. In this case, our mole ratio was 6:1, so that we know that we have 0.0595 moles of silver present in our sample. Once we know the number of moles present, we need to multiply by the molar mass of silver, 107.87, to determine that we had an initial amount of 6.42 grams of silver present in our ore. So as you can see, redox stoichiometry is very similar to regular stoichiometry that you've been doing in previous courses, except that we need to determine the balanced chemical equation for our redox reaction first. Let's try a second example. Here we're asked to find what volume of concentrated nitric acid, HNO3, would be required to dissolve a 3.23 gram of a copper penny. So remember, back in the day where pennies were used, they were made of copper. So the first thing we need to do is to determine the balanced chemical equation. We have nitrate, NO3, we have an acidified solution, H, we have water, and of course we have the copper from the penny. We find that the nitrate is our oxidizing agent, as along with H, as well as water. Water is also a reduction agent, as well as the copper. However, we determined from our table of reduction half reactions that an acidified solution of nitrate is our strongest oxidizing agent, and our copper is going to be our strongest reduction agent. So let's write out the half equations for those on the next slide. Reading our table of half reactions, we find that 2 nitrates react with 4 hydrogen plus 2 electrons to give you nitrogen tetraoxide and 2 waters, whereas copper solid oxidizes to copper 2 plus ion and 2 electron. Luckily for us, the number of electrons involved in the reduction reaction and the oxidation reaction is both 2. We don't need to find the lowest common multiple. All we need to do is add our 2 equations together, and here is our final equation. So we go back to the question. We wanted to know what volume of a concentrated nitric acid solution was needed to dissolve a 3.23 gram penny. The first thing we need to do is to convert grams of copper into moles of copper. We do this by dividing by the molar mass, and we find out we have 0.0508 moles of copper. Then we use our mole to mole ratio that we determined from our balance coefficients in our balance equation, and it was 4 to 1. We find that we actually need 0.203 moles of nitrate. And now going back to our concentration formula, where V equals N divided by C, N being the moles of nitrate that we need, C is our concentration of concentrated nitric acid. We do our math, and we find that we need 13.2 mils of our concentrated nitric acid to dissolve 3.23 grams of copper. So once again, once you're able to determine the coefficients in the balanced chemical equation for a redox reaction, the stoichiometry is very similar to all the stoichiometries you've been doing in your previous courses.